from the title, Elementary Matrices, you may have gotten the impression that I somehow had the tapes out of order. We've talked about some fairly complicated matrices. Today we're going back to something called elementary. Well, actually the word elementary doesn't mean easy or the beginning. The word elementary in this case simply means matrices derived from the elementary operations. So recall the elementary row operations for matrices. One is you can interchange any two rows. You can multiply a row by constant. You can multiply a row by constant and add to another row. Those are your elementary row operations. Okay, let's start with the definition of an elementary matrix. A square matrix is elementary if it can be obtained from I meaning the identity matrix, by a single elementary row operation. So in order to be elementary, the matrix first of all must be square. Next, it must be obtained from the identity matrix by single elementary row operation. Interchange two rows, multiply row by constant, multiply by constant, and add to another row. The matrix 1, 0, 2, 1 is elementary. Now see if you can figure out, before I show you on the screen, see if you can figure out why it's elementary. In other words, what did you do to the identity matrix to get 1, 0, 2, 1? The identity matrix is 1, 0, 0, 1. What did you do to the identity matrix to get this one? If you can go from the identity matrix to this matrix in one step, then it is elementary. Well, it's elementary because from the identity 1, 0, 0, 1, row 1 was multiplied by 2 and added to row 2. So if we go back, multiply row 1 by 2, that would be 2, 0, and add to row 2. 2 plus 0 is 2. 0 plus 1 is 1. So it only took one row operation to get the matrix from the identity. So therefore it is elementary. One, 0, 0, 0, 2, 0, 0, 0, negative 1 is not elementary. The reason it's not elementary is that it takes two operations to transform I into the matrix. So if we think about I, 1, 0, 0, 0, 1, 0, 0, 0, 1, I have to do two things. I have to multiply row 2 by 2. I have to multiply row 3 by negative 1. So it takes two operations to transform I into this matrix. Therefore, this matrix is not elementary. Now we're getting to a very important fact with elementary matrices. That E be the elementary matrix obtained by performing an elementary row operation on I. if that same operation is performed on A, then the resulting matrix is given by the product E times A. Again, E is an elementary matrix obtained by performing an elementary operation on I. So we know what E is. We can look at E, look at I, and determine what operation was performed on I to get E. If that same operation is performed on matrix A, then the resulting matrix is given by the product EA. I'm going to just note once that dimensions must be such as to allow multiplication. So for all these properties, the dimensions of the matrix must be such that matrix multiplication is possible. Let me illustrate this very important fact by example. Look at matrix A. Matrix A is the matrix 4, 1, 5, 0, 1, 0, 3, 2, 7, 4, negative 3, 1. Now if I multiply row 2 by negative 7 and add to row 3, I get matrix B. So we performed the elementary row operation, which was to multiply row 2 by negative 7 and add to row 3. So I left 1 the same. Negative 7 times 1 is negative 7, plus 7 is 0. Negative 7 times 0 is 0. 0 plus 4 is 4. Negative 7 times 3 is a negative 21. Negative 21 plus a negative 3 is negative 24. Negative 7 times 2 is negative 14. Plus 1 is negative 13. So we multiplied row 2 by negative 7, we added to row 3. Now I'm going to do that same operation to the identity and get an elementary matrix. So I'm going to start with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and I'm going to multiply row 2 by negative 7 and add to row 3. Negative 7 times 0, 0, 0 plus 0, 0. 1 times negative 7 is negative 7. Negative 7 plus 0 is negative 7. Negative 7 times 0 is 0. 0 plus 1 is 1. So E is the elementary matrix obtained by multiplying row 2 of the identity by negative 7 and adding to row 3. Now by the theorem, we know that matrix B is equal to E times A. Well, let's see if that is indeed the case. Notice what E is. 1, 0, 0, 0, 1, 0, 0, negative 7, 1. So, I'm writing E down. 1, 0, 0, 0, 1, 0, 0, negative 7, 1. That's E. Times A. Let's go back. A was 4, 1, 5, 0, 1, 0, 3, 2, 7, 4, negative 3, 1. Now if I multiply E times A, according to the theorem, I should get B. Well, let's do the multiplying, then we'll go back and see if we did indeed get B. Okay, so I need to multiply. So we'll do row 1 with the column 1. That would be 4 plus 0 is 4. That would be 1 plus 0 is 1. 5 plus 0 is 5. 0, 0, 0 is 0. Now, of course, it's going to be 0 plus 1 plus 0, so that would be 1. 0, 0, 0, 0, 3, 0, so that's 3. 0, 2, 0, so that one is 2. Now for row 3, column 1, that's 0, negative 7 plus 7, 0, 0, 4, 0, negative 15, 0, negative 7 times 3 is negative 21, minus 3 is negative 24, 0, negative 14, 1, adds to negative 13. So here should be B. You go back, or you can go back and look in your notes and see if that was indeed matrix B. So we have B was 4, 1, 5, 0. It's hard to get them both on there at the same time. One, 0, 3, 2, 0, 4, negative 24, negative 13. So you can see that the example did illustrate the theorem. Now remember, an example never proves anything, but you can use it to convince yourself that it's true. Elementary matrices have some interesting properties that make life easier for us later. Let E be an elementary matrix. E inverse exists and is itself an elementary matrix. So if E is an elementary matrix, then E has an inverse, and the inverse is itself an elementary matrix. To get the inverse, simply reverse the elementary operation used to get E from I. If E is elementary, that means you did a row operation to get E, so reverse that operation and you'll get E inverse. Okay, let's look at E. E is 1, 0, 0, 0, 1, 0, negative 2, 0, 1. Now what was done to I? 1, 0, 0, 0, 1, 0, 0, 0, 1. What was done to I to get E? Well, we can tell that E was obtained by multiplying row 1 by negative 2 and adding to row 3. So negative 2 times 1 is negative 2, plus 0 is negative 2. Negative 2 times 0 is 0. 0 plus 0 is 0. Negative 2 times 0 is 0. 0 plus 1 is 1. So that's how we got E. Well, if we reverse it, then we would multiply row 1 by positive 2 and add to row 3. I wrote that down for you. So to get E inverse, multiply row 1 on the identity by positive 2 and add to row 3. Again, the identity is 1, 0, 0, 0, 1, 0, 0, 0, 1. So if I multiply row 1 by positive 2, reversing what I did to get E, I'll get E inverse. Leave the first row the same, leave the second row the same. 2 times 1 is 2. 2 plus 0 is 2. 2 times 0 is 0. 0 plus 0 is 0. 2 times 0 is 0. 0 plus 1 is 1. By finding the inverse by the regular method, one can see why the simple reversing of operations works. So we have the regular method is to write matrix E on the left, 1, 0, 0, 0, 1, 0, negative 2, 0, 1, and write the identity on the right. And we want to transform the left part into the identity. Remember, that's how we find the inverse. Transform the left part into the identity using the elementary matrix operations. Well, everything fits except this point, so all I need to do is to multiply row 1 by positive 2, add to row 3. So leave row 1 the same. Leave row 2 the same. But multiply row 1 by 2 and add to row 3 to get the third row. 2 times 1 is 2, plus negative 2 is 0. 2 times 0 is 0. 0 plus 0 is 0. 2 times 0 is 0. 0 plus 1 is 1. 2 times 1 is 2. 2 plus 0 is 2. 2 times 0 is 0. 0 plus 0 is 0. 2 times 0 is 0. 0 plus 1 is 1. So here's going to be E inverse. So you can easily see why that if you simply reverse the process, you'll get E inverse, because you are going back and making sure you have the identity on the right side, which means to get the identity, you'd have to reverse the process that was used to get E. Now we're ready to start the key to today's lesson. Write 1, 2, 3, 2, 5, 6, 1, 3, 4 as a product of elementary matrices. So the way I'm going to write it as a product of elementary matrices, I'm going to reduce the matrix, and I'm going to keep track of the elementary matrices. So we'll reduce the matrix. We'll keep track of the elementary matrices. So over here on this side, I'm going to write where I reduced it. Here, I'm going to write the elementary matrix. Now the first thing I'm going to do to reduce it is multiply row 1 by 2 and add to row 2. So we'll multiply row 1 by negative 2. I believe I said 2, I mean negative 2. I've got to get a 0 here. Add to row 2. Leave the first row the same. So with E1, see, E1 is what I do to the identity. So I start with 1, 0, 0, 0, 1, 0, 0, 0, 1. So I'll start with the identity, and I'm going to do the same thing to E, the identity, I'm going to do the same thing to the identity to get E that I do over here. Well, we're multiplying row 1 by negative 2, adding to row 2. Negative 2 times 1 is negative 2. plus 2 is 0. Negative 2 times 2 is negative 4, plus 5 is 1. Negative 2 times 3 is negative 6, plus 6 is 0. Then I'll leave row 3 the same. Now we're going to do the same thing to the identity matrix. Leave row 1 the same. For row 2, I multiply row 1 by negative 2 and add to row 1. If I go to the identity matrix, 2 times negative 1 is negative 2, plus 0 is negative 2. 2 times 0 is negative 2 times 0 is 0, plus 0 is 0. Plus the identity matrix is going to be plus 1 here. And negative 2 times 0 is 0, plus 0 is 0. See, the identity, let me write it here real small, is 1, 0, 0, 0, 1, 0, 0, 0, 1. So to get E1, I go to the identity matrix and do the same thing I did up here. Multiply row 1 by negative 2 and add to row 2. Negative 2 times 1 is negative 2, plus 0 is negative 2. Negative 2 times 0 is 0, plus 1 is 1. Negative 2 times 0 is 0, 0 plus 0 is 0. And I'll leave row 3 the same. Now I'm going to multiply row 1 by negative 1, add to row 3. So leave 1 the same, leave row 2 the same, but I'm going to multiply row 1 by negative 1 and add to row 3. Negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 2 is negative 2. Negative 2 plus 3 is 1. Negative 1 times 3 is negative 3. Plus 4 is 1. Now to get E2, I'm going to do the same thing to the identity matrix that we did to the matrix on the left. What do? I multiply row 1 by negative 1 and add to row 3. So I'm going to leave rows 1 and 2 unchanged. 1, 0, 0, 0, 1, 0. Going back to the identity now. I'm going to do the same thing to the identity matrix that I did to the matrix on the left. So with the identity matrix, I'm going to multiply row 1 by negative 1 and add to row 3. Negative 1 times 1 is negative 1, plus 0 is negative 1. Negative 1 times 0 is 0, 0 plus 0 is 0. Negative 1 times 0 is 0, 0 plus 1 is 1. Continuing in the reduction process, I'm going to multiply row 2 by negative 2, add to row 1. So I'll just write down rows 2 and 3. I'm not doing anything to them in this step, but I'm multiplying row 2 by negative 2 and adding to row 1. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2. Plus 2 is 0. Negative 2 times 0 is 0. 0 plus 3 is 3. So for E3, I'm going to do the same thing to the identity matrix. The identity matrix has 0, 1, 0, 0, 0, 1. And I'm going to multiply row 2 by negative 2 and add to row 1. Well, row 1 in the identity matrix is 1, 0, 0. So negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2 plus 0 is negative 2. Negative 2 times 0 is 0 plus 0 is 0. Okay, continuing with the reduction process, I need to multiply row 2 by negative 1. Add to row 3, because I need a 0 down here. So I'm going to write the 1, 0, 3, the 0, 1, 0. Now multiply row 2 by negative 1, add to 3. Negative 1 times 0, 0. 0 plus 0, 0. Negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 0, 0. 0 plus 1 is 1. So then E4, I'm going to do the same thing to the identity matrix. I'm going to leave rows 1 and 2 of the identity matrix the same, but I'm going to multiply row 2 by negative 1 and add to row 3. Well, row 3 of the identity matrix is 0, 0, 1. So I multiply row 2 by negative 1 and add to 3. Negative 1 times 0, 0. 0 plus 0, 0. Negative 1 times 1 is negative 1, plus 0 is negative 1. Negative 1 times 0, 0. 0 plus 1 is 1. So we get E4. I'm almost through reducing this one. All I need to do is multiply row 3 by negative 3, add to row 1. So I'll leave row 2 and row 3 the same. I'll multiply row 3 by negative 3 and add to 1. Negative 3 times 0, 0. 0 plus 1 is 1. Negative 3 times 0, 0. 0 plus 0 is 0. Negative 3 times 1 is negative 3, plus 3 is 0. Doing the same thing to the identity matrix, I get what E5 is. So we have 0, 1, 0, 0, 0, 1. And we multiply row 3 by negative 3 and add to 1. Negative 3 times 0, 0. 0 plus 1 is 1, because remember 1 is in the identity. 0 times negative 3 is 0, plus 0 is 0. Negative 3 times 1 is negative 3, plus 0 is negative 3. Okay, now let's put the chain together to see what happens. We have I here, and how did we get I? Well, to get I, we started with A, and by the theorem that we illustrated by example, we can, to get I, we took the A, we multiplied it by E1. So E1A, going all the way back up here, if I start with matrix A, multiplied by E1, I'll be to this place. Take this matrix, multiply it by E2, will be to here, multiply it by E3, we'll move down and so forth. You can see what we're doing. So I can get matrix B. Matrix B is equal to the elementary matrix times A. So I ended up with I eventually, but trace it all the way back through the individual parts. After my first transformation, I had E1A, so I had a matrix B1, it was E1A. Then I had a matrix B2, that was E2 times B1. Then a matrix B3, that was E3 times B2, and so forth, up until finally we got to the identity matrix. But our problem was not to write the identity matrix as a product of elementary matrices. It was to write the matrix. So I need to get A as a product of elementary matrices. Well, to get A, what I'm going to start doing is just start multiplying by the inverses. So we have I, and we have A over here. I'm just going to start multiplying by the inverses. If I multiply by E5 inverse, that leaves me with all this. Then I'll multiply by E4 inverse, leaves me with all this. Multiply by E3 inverse, I'm left with this. Multiply by E2 inverse, then multiply by E1 inverse. So we have A is a product of elementary matrices, or A is equal to E1 inverse, E2 inverse, E3 inverse, E4 inverse, E5 inverse, I. And of course I is an elementary matrix in itself. So we have now written A as a product of elementary matrices. Well, there's only one problem with this. We don't have the inverses. All we have would be the matrices. We have E1, E2, E3, E4, and E5, but we don't have the inverses. However, it is a simple matter to go back and get the inverses. We just reverse what we did to get the E's. But here we multiply row 1 by -2 and add it to row 2. If we reverse it, we'll multiply row 1 by +2 and add to row 2. So E1 inverse would be 1, 0, 0, 2, 1, 0, 0, 0, 1. Take the identity, multiply by +2, and add to row 2. 2 times 1 is 2, plus 0 is 0, and so forth. E2 inverse, well, to get E2, we multiply row 1 by -1 and add it to row 3. So if I reverse it, that means I'd be multiplying by +1 and adding to row 3. So it'd be 1, 0, 0, 0, 1, 0, 1, 0, 0. E3 inverse. Well, to get E3, we multiply row 2 by -2 and add it to row 1. So I need to multiply row 2 by +2 and add to row 1. So E3 inverse would be 1, 2, 0, 0, 1, 0, 0, 0, 1. Multiply row 2 by +1, add to row 1. Well, to get E4, we multiplied row 2 by -1 and add it to row 3. So to get E4 inverse, I need to multiply row 2 by +1 and add to row 3. So we have 1, 0, 0, 0, 1, 0, 0, 1, 1. Multiply row 2 by +1, add to row 3. And finally we need E5 inverse. Well, to get E5, I multiplied row 3 by -3 and added 1. So if I reverse it, I multiply row 3 by +3, add to row 1. It would be 1, 0, 3, 0, 1, 0, 0, 0, 1. Now I have E5 inverse, E4 inverse, E3 inverse, E2 inverse, and E1 inverse. So if I have all the inverses, then we indeed have written A as a product of elementary matrices, because from the earlier statement we know that the inverse itself is an elementary matrix. Now we're ready to look at a list of equivalent statements about the things that we have developed. So all these statements are equivalent. The first statement is A is invertible. Well, if A is invertible, that means it has an inverse. Another way of saying that A has an inverse is saying that AX equal B has a unique solution. So if the matrix equation AX equal B has a unique solution, that means A is invertible, which means A has an inverse. Now I really didn't need 3 because 2 and 3 say the same, but if AX equals 0, that means B's equals 0 has only the trivial solution. Well, AX equals 0 would have a solution with X, all the elements being 0 here. Well, that would be the unique one. But anyway, AX equals 0 has only the trivial solution is equivalent to A being invertible. We already have that A is invertible if A is rho equivalent to the identity matrix. I mean, that's how we inverted it. We transformed A into the identity matrix. So that's the, we already knew that one. And the last one that we're adding to it, A is invertible if it can be written as the product of elementary matrices. One of the more interesting aspects of linear algebra is solving systems of linear equations. The regular row reduction algorithms work well for fairly small systems, 3 by 3, 4 by 4, and so forth. As the systems get larger, the regular algorithm, the row reduction algorithm, takes up more and more computer space. Mathematicians and computer scientists are always interested in more efficient algorithms for solving large systems. Today's lesson will introduce a more efficient algorithm for computer solutions of systems of equations. Now, for hand solutions, the Gaussian elimination or the elementary row operations will continue to be the best and the quickest. But for computer solution, today's lesson gives a more efficient algorithm. A matrix with zeros above the diagonal is called a lower triangular matrix. In other words, if you have zeros above the diagonal, all the non-zero numbers would be on the diagonal or below. So it's called a lower triangular matrix. A matrix with zeros below the diagonal is upper triangular. So if all the zeros are below it, then your non-zero numbers are either on the diagonal or above it. Therefore the name upper triangular. The matrix 1, 2, 4, 0, 3, 5, 0, 0, 4 is upper triangular. If you locate the diagonal, all the entries below the diagonal are zeros. So a matrix with zeros below the diagonal is upper triangular. So this is an upper triangular matrix. If a square matrix A can be written as the product of a lower triangular matrix L and an upper triangular matrix U, then A is equal to L times U is an LU factorization of A. It's just like you factor numbers. I could take 20 and I could write it as 5 times 4. So 5 times 4 is a factorization of 20. It's not a complete factorization, but it is a factorization. So just like we factor numbers, we can go back and factor matrices. I can factor the matrix into a lower triangular matrix times an upper triangular matrix. The following example will illustrate the process that you always follow to find an LU factorization of a matrix. So we want to find the LU factorization of matrix A, which is 2, 0, 0, 0, negative 3, 1, 10, 12, 3. So I want to write A as a lower triangular matrix times an upper triangular matrix. If I simply row reduce A, so I have zeros below the diagonal, then I will have my U, my upper triangular matrix. So as I row reduce it, I'm going to keep up with what I have done with my E's and use the idea that we developed in yesterday's tape to go back and get L. I'll give you a note on that. So what we want to do is to row reduce to create U while keeping track of the elementary operations. So we won't go to A and row reduce to create U while keeping track of the elementary operations. Now to row reduce A, what I need to do is to have zeros below the diagonal. So I need to have a 0 here and a 0 here. I can multiply row 1 by -5 and add to row 3 to create the 0 in this position. So multiply row 1 by -5, add to row 3. So I'll multiply row 1 by -5 and add to row 3. -5 times 2 is -10, plus 10 is 0. -5 times 0 is 0. 0 plus 12 is 12. -5 times 0 is 0. 0 plus 3 is 3. And of course, I'll leave the other two the same. Now I want to keep track of E1. Now we multiplied row 1 by -5 and added to row 3. Remember, E1 is in reference to the identity. So the identity is 1, 0, 0. Row 1 by -5 and add to row 3. -5 times 1 is -5. -5 plus 0 is -5. -5 times 0 is 0. 0 plus 0 is 0. -5 times 0 is 0. 0 plus 1 is 1. Now while I'm here, I'm going ahead and write E sub 1 inverse. Now to write the inverse, I simply reversed the row operation that gave me E1. So I'd multiply row 1 by +5 and add to row 3. So leave rows 1 and 2 the same. And multiply row 1 by -5 and add to row 3. I'm going to reverse this. So multiply row 1 by +5 and add to row 3. 5 times 1 is 5. 5 plus 0 is 5. 5 times 0 is 0. 0 plus 0 is 0. 5 times 0 is 0. 0 plus 1 is 1. So here is E inverse. I reversed the operation that gave me E. To get E, I multiplied row 1 by -5 and added to row 3. To get E inverse, I reversed it, multiply row 1 by +5 and add to row 3. Now let's go over and continue with the row reduction. I need a 0 here. So what I would need to do is multiply row 2 by +4 and add to row 3. So we need to multiply row 2 by 4 and add to row 3. We'll leave the first the same, 2, 0, 0. Leave the second the same, 0, -3, 1, but multiply row 2 by 4 and add to 3. 4 times 0 is 0, 0 plus 0 is 0. 4 times a -3 is -12, -12 plus 12 is 0. 4 times 1 is 4, plus 3 is 7. So your upper triangular matrix is going to be 2, 0, 0, 0, -3, 1, 0, 0, 7. And now we need to get what E2 would be. Well, in reference to the identity matrix, we multiply row 2 by 4 and add to row 3. So leave the first row the same, leave the second row the same, multiply row 2 by 4 and add to row 3. 4 times 1 is 4. Plus 0 is 4. 4 times 0 is 0, plus 1 is 1. While we're here, let's get E2 inverse. Well, we simply want to reverse the operation that gave us E2. Well, to get E2, I'll multiply row 2 by +4 and add it to 3. So if I reverse it, I'll multiply row 2 by a -4 and add to 3. So that's going to be, in the third row, 0, -4, 1. So now the upper triangular matrix, the way we got it, we started with A, then we reduced to, we've got the elementary matrix E1, so E1 times A would give me my intermediate step, and then E2 times the intermediate step will give me the upper triangular matrix. So U is E2, E1 times A. Now to find out what A is, A would be, well, I have to multiply U by the inverse of E2 to eliminate this one. So I'll put E2U would equal to E1A. Now multiply the inverse of E1, I get E1 inverse. E2 inverse U is equal to A. So that means E1 inverse times E2 inverse must be the required L. So we write L is equal to E1 inverse times E2 inverse. Now look back in your notes, and you'll see that E1 inverse was 1, 0, 0, 0, 1, 0, 5, 0, 1. And you can still see E2 inverse. 1, 0, 0, 0, 1, 0, 0, negative 4, 1. Just doing your matrix multiplication. 1 plus 0 is 1. 0, 0, 0, 0, 0, 0. 0, 0, 0. 0, 1, 0, 0, 0, 0, 5, 0, 0, 0, 0, negative 4, 0, 0, 1. So here is L. 1, 0, 0, 0, 1, 0, 5, negative 4, 1. So now we have the LU factorization. A is equal to L times U. Now before continuing, make sure you have down the process for finding the LU factorization. You row reduce to get U. As you row reduce, keep up with your elementary operations and create your E1s and E2s and so forth. Well, you're going to need the inverses, so get E1, E2 inverse as you're doing it. And then to get L, you can get L by multiplying the E1 inverse times the E2 inverse times the E3 inverse and so forth. Once you have LU factorization on the coefficient matrix A, you can solve the system AX equal B in 2 concise steps. So before you can do anything else, you have to get the LU factorization. Once you get the LU factorization, you can solve the system AX equal B in 2 concise steps. In step 1, you let y equal to ux and solve ly is equal to b for y. So this is just substitution solving. Step 2, you solve ux equal to y for x. And I gave you a note, AX equal to B implies that LUX is equal to B, because what was A equal to? A was LU, so it's just doing the substitution there. Let's solve 2x equal 8, and negative 3y plus z is equal to negative 7. 10x plus 12y plus 3z is equal to 82. Well, let's write in the form ax is equal to b first. Well, your A matrix will be your coefficient matrices, which would be, or your coefficient matrix, which is 2, 0, 0, 0, negative 3, 1, 10, 12, 3, that's A. X will be your variables, X, Y, and Z is equal to B, which will be your constants, 8, negative 7, 82. So A is your coefficient matrix, B is your column matrix of variables, and C is your column matrix of constants. Well, we want, the first step is to get an LU factorization of A. Well, we've already done that. I gave you an example here that would match the work we've already done, because notice the A we used before, 2, 0, 0, 0, negative 3, 1, 10, 12, 3. It was the same matrix. So we already know the LU factorization of it. So that would be the A would equal to 1, 0, 0, 0, 1, 0, 5, negative 4, 1. And here's your lower triangular matrix times the upper 2, 0, 0, 0, negative 3, 1, 0, 0, 7. Now the two steps that we said follow once you have the LU factorization is to let y is equal to ux. So we'll let y, which I'll call x prime, y prime, z prime. So the y matrix, make it capital Y. The y matrix, which is x prime, y prime, z prime, is going to equal to ux. So that would be 2, 0, 0, 0, negative 3, 1, 0, 0, 7, and x is x, y, z. So we're not going to do anything with this at the time except just let u equal to it, or let y equal to ux. That's all we're going to do now. What we're going to solve is we're going to solve Ly is equal to B. Well, L is your matrix 1, 0, 0, 0, 1, 0, 5, negative 4, 1. So L is lower triangular because all zeros above the diagonal times the y, x prime, y prime, z prime is equal to B, which is your column matrix of constants, 8, negative 7, 82. Now I have the equation x prime, the equations, the system, x prime is equal to 8, y prime is equal to a negative 7, 5x prime minus 4y prime plus z prime is 82. See, that's just matrix multiplication. 1 times x1 plus 0 is equal to 8. 0 plus y prime plus 0 is equal to negative 7. 5x1 minus 5x prime minus 4y prime plus z prime is equal to 82. Now this is very easy to solve for x prime, y prime, and z prime. Now it may not always be as easy as mine, but back substitution is all you'll ever need. I know x prime, I know y prime. So if x prime is 8, that means I have 40, plus y prime is negative 7. Negative 4 times negative 7 is 28, plus z prime is equal to 82. 68 plus z prime is 82. Z prime is 14. So we have that y is equal to the column matrix x prime, y prime, z prime, which is 8, negative 7, 14. Now, the next step says solve ux equal to y for x. So go back to my upper triangular matrix. 2, 0, 0, 0, negative 3, 1, 0, 0, 7. So that would be u, x, or solve for ux is equal to y. So x would be x, y, z is equal to y that we've just solved for, which is 8, negative 7, 14. Okay, write this out in equation form, and we can solve this by simple back substitution as well. 2x plus 0y plus 0z, so I get 2x is equal to 8. 0x minus 3y plus z is equal to a negative 7. 0x, 0y, 7z is equal to 14. Now in general, this last equation will always just involve z. The second will involve y and z, and the first will involve x, y, and z. But we can easily back substitute. This case is even easier. I see 2x is equal to 8, so that means x is 4. 7z is equal to 14, so z is 2. And getting the y, we have that a negative 3y plus z plus 2 is equal to negative 7. So I have a negative 3y is equal to negative 9, or y is 3. So I can get that x is going to be 4, 3, 2. Or I can say that little x is 4, little y is 3, little z is 2, and you have the solution to the system of equations.